So for this part, I'm going to talk about a recent work for Keyphrase generation. And maybe you can see that one problem I'm always trying to resolve is how to get rid of the data annotation for key phrases. How can we reduce the effort on the human? So that's why I have presented work based on the unsupervised method for key phrase for the key phrase generation, as well as the retrieval augmented key phrase generation. And for this work, is another study in a similar manner, but here I want to investigate what kind of Keyphrase generation models can be adapted to a new domain with really not too much annotation. All right, so very quick review of what we have seen for Keyphrase generation. Most models still need a lot of annotation to train such a good model to perform well in a certain domain. But one may think that, so if we train a model in domain A, can the knowledge learned in this data of the domain A transferable to other domains? So here, in order to answer this question, we collected the 4 large data sets in different domains, and which had already been introduced by Debuggy. And now we also consider a base transformer, which is randomly initialized, and a large transformer initialized with a pre-trained BART. And we want to see, okay, if we train it in domain A, how it performs in another domain. And this heat map shows that, we see along the diagonal, all the models perform super well for in-domain cases, but for the cross-domain evaluation, usually it performs super poorly. Even with the pre-training of a large even we initialize the model with BART, which is pre-trained with a large scale of data. Though in most cases, the scores are getting better, but still in terms of cross-domain generalization, we can still observe a huge gap between the in-domain performance and the cross-domain performance. And this result suggests that the key phrase knowledge does not transfer very well across domains. What's the reason? So to understand why they fail, I inspect the phrase vocabulary in each domain and trying to visualize their overlap in this one diagram. And you can see between those domains, there's only a small overlap. And this suggests that each domain is actually speaking in their own languages. So they only care about the specific set of key phrases in that domain. And I also tried to visualize the phrase embedding in this semantic space. So each phrase is represented by bird. And you may see that the distribution of the OpenKP is the most widespread, and it has a really large overlap with the other domains, since all its documents are collected from the web. But for the KP20K and the stacked exchange, so one is from the paper, one is from the online QA forum, they overlap very much. But for the KP Times, which mostly about the news articles, it's really, it only overlaps with overlaps with OpenKP. And the degree of the overlaps actually correlates very well with the results we have seen here in the transferable experiments. Okay, so these results, this analysis as well, motivates us to build models which are dedicated to each target domain. And we hope to use the annotated data as little as possible. And recall that the structure of the language, such as the syntax and grammar, is generally universal. So whether we can exploit the phrase or annotation on the internet to pre-train a domain general model and see whether it can transfer well to some other specific target domain. All right, so this is the resources we will be considering for this study. The first one is a huge general domain dataset with noisy phrase annotation. And we are considering 3 domains. For each domain, we have a large data set in the specific domain without annotation, and a small data set for each domain with annotation. And the method we are considering is, okay, inspired by the success of the pre-trained language model, such as T5 and BERT, can we think of a way to pre-train a model using large scale of open domain phrase data, and to let the model be aware of how phrases are like in the real world? And in the second stage, we want to adapt the first stage model to a target domain using this large amount of unannotated data in each domain. And the third stage is just fine-tuning. So we'll just utilize the small amount of annotated data to obtain the final models. And this outlines the method I just described. And we will dive into the details of each step, how they are implemented specifically. And for the first stage, our goal is to pre-train a Keyphrase generation model with the general domain knowledge. And here, we just resort to the weak annotations in the Wikipedia text for this purpose. And to be specific, the anchor text as well as the bold text, usually they are well-formed concepts or entities. And also the wiki text contain the category information that also play a very similar roles as the absent of key phrases we've been discussing all the time. And then we just convert those Wikipedia passages into the source target pairs. And in this way, we can just train a sequence-to-sequence model with this Wikipedia data. And let's come to the second stage. Now we already have a pre-trained domain general model. But how can we adapt it to a target domain without annotation? And so recall that it's really relatively easy to collect a large amount of data in a target domain without annotation. We can just utilize the pre-trained model to generate the pseudo phrases on those large data sets and annotated data sets, resulting in many pseudo-labeled document key phrase pairs. And we call this method transfer labeling. And then the second step in the stage 2 is to just, given the models we have from the stage 1, or a completely brand new model, and to just adapt them to the target domain with the pseudo document phrase pairs we have just generated in the last step. So different from the stage 1, which the model learns the general domain phrase knowledge. Here you can see it's the goal of the stage 2 is also a pre-training, but it's more domain specific. And then in the stage 3, we can get given the model checkpoint from stage 2, we'll just fine-tune the model and we will get the final model. And one thing I want to highlight is in order to test the model's performance in a new domain without too much annotation, we just adopted a setting, a few shot learning setting by utilizing only 100, 1,000, and 10,000 annotated data for the third stage fine-tuning. All right, so the first result I would like to check out is the zero-shot performance of our stage 1 model. So from the scores here, we can see that the model trained with the wiki phrases can achieve really decent zero-shot performance on each targeted domain. So those scores are not really perfect, but I think they are good enough to serve as pseudo phrases for the domain adaptation in the second stage. And it's also interesting to see that the large model initialized with BART doesn't necessarily perform better than the base transformer that is trained from scratch. And let's take a look at some real examples. So the wiki concept trained model can produce some phrases really relevant. So for example, in this one, the model infers many phrases that are relevant to the personal financial issues. And in another example, the model successfully predicted many relevant entities. But it also predicts something really wiki style, such like this, the computer company of the United States. Okay, then let's move ahead to another result. So here I would like to compare different strategies for the stage 2 domain adaptation to see how well the proposed transfer labeling works comparing to some simple strategies such as non-phrases and random spans. And so this figure shows that the domain adaptation with the transfer labeling does outperform the non-phrases by a really large margin. But in general, it performs worse than the random span. So this might be because we trained the transformer from scratch, and the random span training can lead to a more robust result than the other two strategies. But clearly, the random span itself does not capture all the important information in the context. And you can see by merging the transfer labeling and the random spans, the models gain a larger performance boost, as you can see here. And we will just use this half and half strategy in the following results. Okay, so this is a major result. We'll just say by combining different stages of training and how they perform in this few shot setting. I know that since the data size of each domain is different, so for a fair comparison across different domains, we just use 100,000 documents in each domain for the second stage training. All right, so this is the main result I'll talk about. And from the figure, we can observe that by stacking the multiple stage training, the performance is generally getting better across domains. So indicating the effectiveness of the proposed domain adaptation methods. And if we just take a look at some detailed results, So for the open KP and the KP times, we all observed a big leap in performance by adding the PT stage, which is the pre-training stage, the pre-training plus the fine-tuning. And this is because the stage one used the whole Wikipedia collection for the pre-training. Therefore, the model is expected to acquire a way better language modeling ability than the models just with fine-tuning and the domain adaptation plus the fine-tuning. And another interesting finding is the gain of the second stage domain adaptation is very, very significant on the stack exchange. So this can be explained by the fact that there's a huge semantic gap between the Wikipedia and the stack exchange. So by adopting the domain adaptation, it can bridge the gap between the two domains and leads to a really significant improvement as shown here. Okay, and since we are short of time, and I'll just stop here. And debugging will talk about learning better keyphrase representations for the next part. So now you have the stage.